this video lecture, we are going to start with section 3, which is having a notion about the zeros of an analytic function. Suppose if we have two polynomials p of z and q of z, we are going to use the division algorithm and divide p of z with respect to q of z, and then you get the form p of z is equal to some polynomial s of z into q of z plus r of z, where both of them s and r are polynomials. Obviously the degree of r of z should be less than the degree of q of z. So suppose if p of a is equal to 0, so we are substituting a here and we know that p of a is equal to 0. So what you get is r of a is equal to 0, right? uh, when p of a is equal to 0, we can choose the linear factor z minus a for this q of z, because z minus a divides p of z, because p of a is equal to 0. So you get p of z is equal to z minus a into s of z plus r of z, and definitely this r of z must be a constant polynomial, because here we are having the linear factor and here the degree will be just 1 less than the degree of p of z. So this r of z must be a constant polynomial, and when we are letting z is equal to a, we already know p of a is equal to 0. So you will obtain p of a and r of a is equal to 0. When you substitute a here, okay, so you get p of a is already 0, then you have the whole of this term to be 0, then r of a is equal to 0. So in total you get 0 is equal to p of a is equal to r of a. So you have the conclusion that p of z is equal to z minus a into s of z, and when s of a is equal to 0, you know that the linear factor z minus a can be taken out from this s of z. So we can factor s of z as z minus a into something, right? So after doing this process for a while, you get p of z is equal to z minus a the whole raised to m into some polynomial t of z, where this m is the value which is coming inside 1 and the degree of p of z, and t of z is a polynomial such that t of a is not equal to 0. That is, no more linear factors can be taken out of this t of z. Also, the degree of t of z will be equal to the degree of p of z minus this m, right? So the next definition is how we define 0 of a function with a particular multiplicity. Suppose if we have a function f from g to c, which is analytic, and a is a point inside g satisfying f of a is equal to 0, then a is a 0 of f of multiplicity m greater than or equal to 1 if there is an analytic function g from g to c such that f of z is equal to z minus a the whole raised to m into g of z, where g of a is not equal to 0. So that is the definition of 0 of f with multiplicity m. Now suppose n is the degree of the polynomial we are talking about. So we have the function p of z, okay. So p of z is a polynomial, and if a1 etc ak are distinct zeros of p of z, then p of z can be definitely written as z minus a1 the whole raised to m1, where m1 is a multiplicity of a1 etc, set minus ak the whole raised to mk into s of z, where s of z is a polynomial with no zeros, and this a1 etc ak are the zeros, distinct zeros of p of z having their respective multiplicities m1 etc mk. And that leads to the movement towards the proving of fundamental theorem of algebra, which says that a polynomial with no zeros is a constant. So let's move on to that. Also, we know what is an entire function is. Entire function is a function which is analytic in the entire complex plane C. That's why it's called the called by the word entire. It's analytic everywhere. And for an entire function, definitely we know that every analytic function has a power series representation expansion. So definitely an entire function also has a power series expansion, which is f of z is equal to summation n is equal to 0 to infinity an z raised to n with infinite radius of convergence. So it is having the radius of convergence to be infinity. So entire functions can be considered as polynomials of infinite degree. Now let's move to what is called the Liouville's theorem. Liouville's theorem is a famous theorem which you might have already encountered before proving, and the proof seems to be very simple, but actually we had worked out a way lot to reach here. So that is the importance of this Liouville's theorem. It says that whenever a function is bounded and entire, then the function has to become a constant. So suppose the function we are talking about is bounded for our z in C. Okay, modulus of f of z is less than or equal to capital M. Okay, and we are assuming that it is entire. Okay, we have to show that it is constant. We are going to show that f dash of z is equal to 0 for every z in C. For that, we are going to use Cauchy's estimate. What was Cauchy's estimate? Cauchy's estimate says that if the function is analytic in open disk BA of R, and if it is bounded like this, then modulus of the nth derivative of f at A is less than or equal to n factorial into m divided by r raised to n, where this A is the center of the open disk we are talking about. Okay, so here we just need the value of n to be 1. We are thinking about modulus of f dash of z. Okay, since here the function is entire, we can take it to be an arbitrary z instead of this a, right? uh, because we are considering the whole of the complex plane, and with the radius can be taken infinite. Okay, so here, when we substitute n is equal to 1, you get modulus of f dash of z is less than or equal to m by r, and r is chosen to be arbitrary because it is entire. You get that this m by r will move towards 0. That means modulus of f dash of z is less than or equal to 0. That means f dash of z is equal to 0 for every z belongs to C. That means f is a constant. And then we move on to the fundamental theorem of algebra, which says that if P is a non-constant polynomial, then there is a complex number A with P of A is equal to 0. So for every non-constant polynomial, there will exist a root, or we can factorize it. So let's move on to the proof. So for that, we are assuming that the polynomial we are talking about is not equal to 0 for all z belongs to C. Then we are defining a function f of z is equal to 1 by p of z. It can be defined, it is well defined because p of z is never 0. Then f is an entire function because the denominator is never 0, right? So if p is non-constant, assuming p is non-constant, then p of z being a polynomial, it has the form a n z raised to n plus a n minus 1 z raised to n minus 1 plus etc plus a1 z plus a naught. where n is greater than or equal to 1. So limit set tends to infinity, modulus of p of z is considered, and from that the usual limit process you get that is equal to infinity. Okay, that means limit set tends to infinity f of z is equal to limit set tends to infinity 1 by p of z, right? So that is equal to 0 because the denominator is tending to infinity. Therefore, for some r strictly greater than 0, we have modulus of f of z minus 0 is strictly less than 1 for modulus of set strictly greater than r. That is simply the definition of the limit here, because we know that here this f of z is tending to 0. So modulus of f of z minus 0 is made under the epsilon 1. That means for that you will have r such that modulus of r modulus of z is strictly greater than r. That is simply the definition of limit. Now we know that a function is continuous, right? Because we know that a function is the function f is entire, so it will be continuous on closed interval, not on the closed disk b0 r bar, and it being closed and bounded. We know that it is compact. That means the function f we are talking about is uniformly continuous, and using the property of uniform continuity, you get that whenever you have this m strictly greater than 0, there will be mr, you can find m and r such that whenever modulus of z is less than or equal to r, the function modulus of f of z minus 0 is less than or equal to m. So it is not just continuous, it is uniformly continuous. That is what we have taken here. Now, f being an entire function, by Liouville's theorem, we know that here the function is bounded, right? Bounded by either m or 1. Whatever value you can take, whatever is the maximum, you can take that. That means the function will reduce to a constant by Liouville's theorem. So that means f is a constant, which implies p is a constant, but we had taken p to be a non-constant. So you have a contradiction there. So our assumption that p of z is not equal to 0 for all z belongs to C becomes a false statement. So that means p will have some 0 in C. So that is also a very light proof, which is very easy to understand. And from that you have the corollary 3.6, which says that if p of z is a polynomial and a1 etc am are its zeros, aj's are the aj's, each aj's are having multiplicity kj's, then this polynomial p of z can be factorized like this, that is equal to c into z minus a1 the whole raised to k1 etc z minus am the whole raised to km for some constant c, and k1 etc k1 plus etc plus km is the degree of the polynomial p. So that's all for this video lecture. See you in the next lecture. Thank you.